today's lecture, I will be talking about the classification of critical points of functions, and I will be elaborating on some of the topics that we did in the last two lectures. We saw how to understand maxima and minima of functions, okay, in very simple terms. Now, you might have functions that are slightly more complicated than the simple functions that we looked at, and so it's good to have a general idea of how to classify the critical points of functions. So, I will first talk about functions of a single variable, and then I will talk about functions of two variables. Okay. But you can extend these arguments to functions of more than two variables also. Okay. So, let us look at a function of a single variable. So, if you have f of x, okay. Now, a critical point, so critical point implies f prime of x 0 equal to 0. So, if then x 0 is a critical point. So, x 0 becomes a critical point if the derivative at x 0 equal to 0. So, f prime of x 0 is a short notation for dou f by dou x evaluated at x equal to x 0. Okay. Now, that is a critical point. Now there can be different critical points. So, to know nature of critical point, you look at f double prime of x 0. Okay. So, if f double prime of x 0 is greater than 0, then x 0 is a minimum. Okay. And we should emphasize that this is a local minimum, okay, local minimum as opposed to a global minimum. So, suppose you have a function, okay, what we said is that your function can have several minima. So, it can have a function like this. So, now each of these points is a local minimum. So, each of these points, okay, the derivative is 0. Okay. Similarly, you can have local maxima also. Okay. So, each of these is a local maxima. Now, the global minimum of this function is right here. This is the minimum value of the function, but the first derivative will be 0 for each of these. Each of these points will also satisfy minimum conditions. Okay. If f double prime of x 0 is less than 0, then x 0 is a maximum, and again local maximum. If f double prime of x 0 equal to 0, okay, then there are a lot of things that are possible. Okay. What you have to do is to look at f triple prime of x 0. Okay. If then you use the same condition. So, what you will say is f triple prime of x 0 is greater than 0 implies minimum, a local minimum. F triple prime of x 0 less than 0 implies local maximum. Okay. This is if the second derivative is 0. If the second derivative is 0, then you have to look at the third derivative. If the third derivative is 0, you look at the fourth derivative. Okay. So, now what are the kind of functions that can have a second derivative 0, but a third derivative. So, you could have a function something like something that is that comes down and then it goes almost flat for some time. Okay. So, it goes flat enough that the second derivative is 0 and then it goes up again. Okay. So, suppose you just take a function like x minus x cube. Okay. Now, or I will just say x plus x cube or just x cube for that matter. Okay. Now, at x equal to 0, okay, dou f by dou x equal to 0. Should give a little more space here. This is f of x equal to x minus x cube. So, at x equal to 0, dou f by dou x equal to 0, because dou f just say 1 I just say x cube, let me just put it as x cube. Okay. So, let us just take x cube for example. So, at x equal to 0, dou f by dou x is equal to 0, dou square f by dou x square equal to 0, and dou cube f by dou x cube equal to 6 not equal to 0. Okay. This is at x equal to 0, at x equal to 0. At x equal to 0, dou f by dou x is 3x square, because x equal to 0 that is 0, dou square f by dou x square is 6x, okay, which is equal to 0 at x equal to 0, but the third derivative is not 0. Okay. So, clearly this is a local minimum. Okay. So, the point is you have to look at the first non-zero derivative. So, if f prime of x 0 equal to 0, then look at a sign of first non-zero derivative at x 0. Okay. And then you can identify maximum or minimum. To identify a maximum or a minimum, that is a condition for identify maximum or minimum. Of course, if all derivatives are 0, then the function is just a constant. Okay. So, that is a trivial case which I will not bother about. So, this is what you do with functions of single variables. Now, what about functions of many variables, functions of 2 variables? So, the definition of critical point implies f x of x y equal to dou f by dou x equal to at x 0 y 0, at x 0 y 0 equal to 0, and f y of x 0 y 0, and okay, this is very important, both the conditions should be satisfied. So, this and is very important, this which is dou f by dou y at x 0 y 0 equal to 0. Okay. So, that is the condition for the critical point. Now, you can ask the same question, when is it a maximum, when is it a minimum? So, in order to identify maximum or minimum of a function of many variables, what you do is you define f x x, f y y minus f x y, f x y square. Call this as d of x 0 y 0. Okay. So, you are evaluating this at x 0 y 0, all this, each of these derivatives. So, this is nothing but dou square f by dou x square evaluated at x 0 y 0. So, this quantity d, this object d is sometimes called the Hessian. Now, the way you classify the critical points is you say, you look at the first case, if f x x is greater than 0 and d of x 0 y 0 is greater than 0, then this is a minimum and it is a local minimum, again everything is local minimum. Now, the second case is if f x x is less than 0 and d of x 0 y 0 is greater than 0, then it is a local maximum. The third case, so this is if d is greater than 0, you can have two cases where f x x is greater than 0 or it is less than 0. Now, notice the second term in dx y, this is always greater than 0, this is greater than 0, greater than or equal to 0, because it is a square. So, if x x, if d is greater than 0 and f x x is greater than 0, then automatically f y y has to be greater than 0. Similarly, if d is greater than 0, again if f x x is negative, then f y y also has to be negative. So, you can use the same condition even for f y y. Okay, this is only if d is greater than 0. The third case is if d of x 0 y 0 is less than 0, then it is a saddle point. If this is less than 0, okay, then this point is the saddle point. Now notice each of these can be greater than 0, f(x)x), f(y)y) can all be greater than 0 and f(x)y) can also be greater than 0, but if this d is less than 0, then it becomes a saddle point. The fourth case is if d of x0 y0 is equal to 0, then we have to look at higher derivatives. Okay. So, what I want to say is that you have to look at various partial derivatives in order to decide whether you have what kind of critical point you have. Okay. So, now let me just illustrate this with a very simple example of a function, okay, and we will look at this function and we will identify we will list all the critical points and then we will classify them. Okay. So, let us just take a simple example. So, suppose I take f of x y is equal to x cube plus y cube minus x minus y. Okay. So, what are the critical points? So, if you want to identify the critical points, so what you will say is f x, okay, of x0 y0 is equal to x0 square minus 1, and f y of x0 y0, okay. So, the first term is independent of y, so it will not contribute. So, the second term will give 3 y0 square, and then this term x will not contribute. The derivative with respect to y is will be minus 1. So, now at the critical point 3 x0 square equal to 1 implies x0 equal to plus or minus square root of 1 by 3 and y0 equal to plus or minus square root of 1 by 3. Okay. 4 critical points, and what are the 4? So, the first one is 1 by root 3, 1 by root 3. The second one is 1 by root 3 minus 1 by root 3. Third one is minus 1 by root 3, 1 by root 3, and the fourth one is minus 1 by root 3 minus 1 by root 3. This is the value of x0 and y0. So, you have these 4 critical points. Okay, now let us try to classify them. So, let us first we will calculate f(x)x). So, I will do it right here in this f(x)x). Okay. So, first I will write the general derivative, then I will substitute the critical points. So, f(x)x) is equal to 6 x0, f(y)y) is equal to 6 y0, f(xy) is equal to 0. So, f(xy) equal to 0. So, therefore, now you can calculate d of x0 y0 is equal to 36 x0 y0. So, now in the first case and the fourth case d is greater than 0. Now, if you look at the second, if you look at f(x)x) for this, okay. So, f(x)x) is greater than 0. Okay. So, this is clearly a minimum. Okay. Here f(x)x) is less than 0, this is a maximum, and these 2 points have dx for these 2 points d less than 0, and these are saddle points. So, just by looking at the function and taking its derivatives, we identified where it is maximum, where it is minimum, and which are the saddle points of this function. Okay. Now, you can go ahead and if you want, you can actually plot this function using standard plotting software. Okay. So, you can use plotting software especially in multi-dimensional plots. So, plotting software such as MATLAB, Mathematica, GNU-plot, Origin, etc. So, using any of these plotting software, you can actually plot this function and you can actually visualize some of these maxima and minima. So, I encourage you to do this, and this will help you get a better understanding of these critical points. So, I will conclude this lecture here. Okay. So, in the next lecture we will talk about Lagrange's method of undetermined multipliers. Thank you.